In this session, I'll be discussing about statistical modeling. So here, I would not be using any of the R related or any programming language per se, but this is more and more of the conceptual aspects associated with if at all I have to build a statistical model in R or for that matter any kind of package, if at all I have to build a statistical model using the data that I am provided. So this is the typical process. So we would look at what could be the different kinds of statistical methods depending on what kind of data that I have, what are the kinds of objectives that I'm having. Based on this, I am interested in looking at the appropriate statistical methods. Now, once I am given the data and I am asked to go ahead with a statistical model, what are those basic preliminary things that I have to be ready with before going ahead with fitting a model? So in this context, we will understand what do we mean by maximum likelihood and how did this maximum likelihood actually help me in estimating the parameters of a particular model. And we will talk about different types of statistical models, right, including what is the context in which each model would be more and more handy. Now, once I have developed different kinds of models, right? Probably I might have developed a very complex model to start with. So, how do I really simplify the model? What are the various aspects that I look at so that the overall model will be simplified? Then, just as a quick understanding, different kinds of models. Here we have talked about different types of models. So we will look at what is that I can use as formulas in R if I have to fit any of these models. And we will talk about different kinds of symbols we use. Sometimes we use a tilde sign, sometimes we use a product star, sometimes we use colon. So in which cases we use what kind of symbols during the model building process. This is a very important aspect, the box-Cox transformation, right? We will see why do we perform it and what is the major advantage that we are going to get in the modeling process by performing a box-Cox transformation of the data. And then how do I critically evaluate the model? How do I check the model? Once I have prepared, what is the goodness of fit of that particular model? What do I mean by the influence of one or more data points on the model? And how do I really check out for the influence of any of the points on my model? So we will give a quick summary of the various statistical models that we would be using in R for different business purposes, and general functions, if at all. Let's say I am using a linear regression model or a logistic regression model, or for that matter a nonlinear regression model, whatever are the different kinds of models that I am using, or even a neural networks model, any advanced sophisticated models also. Whatever is the kind of model that I am using, what are the kind of the generic functions that are there where I can extract some kind of information about the model. And we would also talk about a few important measures of goodness of the model, or when we are trying to compare model 1 with model 2, some of the measures that we generally look at. So out of which one is called as Akaike information criteria, or generally called as AIC. So we will talk about it, and this is where we will end the session understanding the summarizing the whole statistical modeling process, right from step 1, we'll do a quick summary in terms of what we do if I am given a data and I am asked to go ahead fitting a statistical model to the data. What is that I am going to follow? So once I am clear on this session, then the next part is for what kind of data, what kind of model. But the framework that I apply for all kinds of models will still remain the same. So this session will really help you to get that initial step in terms of applying any kind of model to your data. The process to be followed for almost any kind of a model fitting to your data. So let's get started that way. The most important thing for different objectives, right? I have different business objectives. For each of the objectives, I do a different kind of analysis. So depending on my objective, so I am being given a data or I am asked to do something from the business standpoint, an objective is being provided to me. So for that particular objective, choosing the right kind of statistical analysis is the most critical aspect. So for that, the first thing is I will look at what is the kind of data that I have and what is my objective, what is the kind of question that I want to address. So first frame these things, right? What is the kind of data that you have provided? What is the question that you are supposed to answer? What is your response variable? Right? Response variable is nothing but what is that you want to predict? What is that you want to model? What is that you want to estimate? So that is what will be your response variable. Now, this response variable you are trying to model using your various explanatory variables. So probably it's like price of a product, right? Let's say the price of the car. I want to model the price of the car. So this will become my response variable. But I see that the price could be dependent on, okay, the fuel efficiency of the car. It could be dependent on the horsepower of the car. It could be dependent on, let's say, the length of the car. And it could be dependent on various other aspects. Means this is the response variable, and this response variable is primarily modeled using these various explanatory variables. So I really need to understand what is the nature of this response variable, what is the nature of these explanatory variables. So here in this case, this is a continuous or quantitative kind of a variable. Now I have to see all my explanatory variables also. Are they all continuous, or do I have all of them to be categorical, or do I have them as a mix of both continuous as well as categorical? So that is one more thing that I have to understand from my data. So the response variable wise I have already explained. So whose variation we are trying to understand, we are trying to model. Right? We are trying to predict something. We are trying to understand the variation of the response variable. Generally in my graph, it would be plotted on the y-axis. Whereas the explanatory variables generally are taken on the x-axis. So when I am trying to understand the response variable, the variation in the response variable, I will look at to what extent this variation is taken care of by the variation in the explanatory variable. So by understanding the variation in the explanatory variables, to what extent I will be able to be successful in trying to understand the variation in the response variable. So that is one major thing that we have to be looking at. So we are first identifying what are our response variables, what are our explanatory variables, which would be used for modeling the response variable. What is the nature of each of these variables? So that's one step, the first step. Then understand the way the variables measure. So most commonly, some of them could be continuous measurements, wherein the values could be any real numbers. So I have to see whether each of these variables are continuous variables or categorical variables. Categorical are the factor related variables with two or more levels. So every variable, first thing I have to understand whether the data that has been collected for this purpose is continuous or categorical. Then, before we proceed for doing any kind of analysis, a few questions that we are addressing: which variable do I need to choose as my response variable? What are all the explanatory variables do I have? Is it one, more? What are the types of the explanatory variables? So each explanatory variable, is it continuous, categorical, which means the overall set of explanatory variables, are they a mix of both continuous as well as categorical? And what is the type of response variable? So explanatory variables, I will check whether they are continuous or categorical. Similarly, the response variable also I will look at, is it a continuous, or in some cases it could be a count, it could be a proportion, it could be the time related. So I have to really check what is the nature of my response variable. Does it fall into any of these categories? So that is one more thing that I have to understand before getting started with the statistical modeling analysis as such. And understanding the different statistical methods. So these would be dealt separately in different sessions. Each of these statistical methods which are appropriate for different kinds of data, I will deal with each one of them separately in the next coming sessions. So based on the explanatory variables, we have three major types of models. If all the explanatory variables are continuous, then we will use regression kind of mechanisms. If all the explanatory variables are categorical, the method that we are using is called as ANOVA, or analysis of variance. And if the explanatory variables, some of them are continuous and some of them are categorical, then we would use a mix of both regression and analysis of variance, which is otherwise called as ANCOVA, analysis of covariance. So depending on our explanatory variables, depending on the nature of the explanatory variables, I would be choosing whether I should go with a regression models or ANOVA model or an ANCOVA model. Then based on the response variable also, we have different kinds of statistical methods. If my response variable is a continuous variable, then these are the three methods. So depending on the explanatory variable, I'll use a regression, otherwise called as linear regression. If the response variable is continuous and the explanatory variables are categorical, I'll use ANOVA, and here I'll use ANCOVA. So if the response variable is continuous, I'll use one of these three methods. But if the response variable is proportion, right, I'm trying to model the proportion of defaults. So the proportion, the percentage, then we are modeling what is called as a logistic regression. Right, if my objective is to model a proportion, probability, such kind of stuff, where the value will lie between 0 and 1, then we are trying to model it as a logistic regression model. If my objective is to model the counting of some variables, then we will be using log linear models. So we will be using all these models in our next session. But wherever we are modeling the counting data, we would be using log linear model, where I have to model binary data. The response variable has only two outcomes, 0 and 1, yes or no kind of outcomes. Then we would be using binary logistic regression to model that kind of a data. And similarly, if my response variable is time to maturity, time to death kind of stuff, then we are using the survival analysis model. So these are the different kinds of models that I can use in the statistical modeling. So we would be spending one session each separately for each of these methods so that we get a good hang. But this is a kind of a big primer which you have to be comfortable with. If my explanatory variables are like this and if my response variables are like this, I should be in a clear position to understand which method is more and more appropriate for my data. And in all these things, the simple fundamental is I have to determine the value of the parameters. So every model is a kind of a formula here. So in this formula there will be a few unknowns which are what we are calling as parameters. Based on the data, we are determining the values of the parameters of a particular model in such a way that the data will be fitting to the model. This chosen model will be a best fit to the data. So whatever the model that I am choosing, I will have to determine the parameters of the model in such a way. This is what is called as the maximum likelihood. I have a data with me. I'm choosing, let's say, this model, regression model. Now regression model will be of the form, let's say, y equal to a plus bx. Now y is my response variable, x is my explanatory variable. I have to determine these values a and b. These are called parameters which are unknowns. I have to determine this a and b from the data itself in such a way that this particular model will be a best fit to the data that we are having. So the model is being fitted to the data and I require the minimal adequate model to describe the data. And when we are saying this model should be a best possible fit, we are measuring it in terms of least unexplained variation, which is otherwise like the error associated with that particular model, or when I am using the word error here, the difference between the predicted values and the actual values, the deviation of the predicted values from the actual values should be the minimum most possible. And all the parameters of the model, in this case A and B, they all need to be statistically significant. In that case, we say that the model that we have fitted is a best fit model to the data. So this is an important framework that we have to keep in mind. One, looking at for what kind of data, what kind of objective, what type of model is very much appropriate. And once we have chosen a particular model and we are trying to fit that model to the data, every model will have a set of parameters to be estimated from the data. The estimates of the parameters of the model should happen in such a way that the variation between the predicted and the actual values, or the predicted and the actual values, will be the least possible stuff. So that's one thing that we have to keep in mind while doing the modeling. Now, once again we have a task of creating a robust statistical model. Before we go ahead in terms of fitting the model to a data, some of the preliminary checks that I have to do, right? Generally our data would be in the form of a spreadsheet, in an Excel sheet. Make sure that that particular spreadsheet, the data is correct both in terms of structure and content. Now, do I have for a particular variable, I check whether all the values are present in the same column or the data is present in multiple columns. Are there any kind of zeros that are there in the Excel sheet? If they are zeros, should they be treated as NAs or should they be treated as zeros? I have to really do some quick groundwork. Every row, does it have the same number of columns or does it have more number? Some rows have more number of columns, some rows having less number of columns. So is it more or less uniform or is it weirdly distributed? Are there any such kind of headings which have blanks in them? Because while bringing them into R, I may have all these kinds of problems and they need to be addressed quite in the beginning itself. So that's where we suggest wherever you are reading something from an Excel sheet, first convert that data into a CSV file, use your read.csv as a function to read that particular data into a data frame in R. And after that, do all kinds of preliminary checks to make sure that your data is copied properly from the spreadsheet into R. For that, you can check the head, which will display the initial few values, the tail, which will display the last few values of the data frame. See if any of these are resulting into any kind of errors. So create one-dimensional plots for every one of the variables. Each single variable, depending on whether it is continuous variable or a categorical variable, have an appropriate plot. If it is continuous variable, you can look out for a box plot for the same, or you can have an index plot. You know what kind of charts you have to plot for what kind of data. And if it is more of a continuous categorical variable, probably you can look out for a bar chart on that kind of a data. So every one variable, create a plot, check for the gross errors in the data. Then you can look out between, you can take two variables at a time. You can use the relationships between the variables, where if they are categorical data, you can do a two-dimensional kind of tables, or you can find different functions across the table using the tapply kind of a function, or you can use a plot function to come out with scatter plot matrices, etc., to understand the relationships between two continuous variables as well. Now, once all this is done, just have a quick thought about what should be an appropriate model now based on the data and the objective. So just understand what all explanatory variables that I have to include into the model. Should the explanatory variables and the response variables be taken in the same way, especially the response variable? Should I take it in the same original way, or should I perform some kind of transformations on it? The transformations in the sense, should I do some kind of a logarithmic transformation or a reciprocal kind of a transformation of that particular data, or for that matter, we will be talking at a later point, we'll use something called Box-Cox transformation. So should I use some such kind of transformations on the response variable? Then what interactions should be included? So when I am saying A is the response variable and B is also a response variable, then should I say A is an explanatory variable, B is an explanatory variable. Should I include another variable called A multiplied by B? That is what we are calling as the interaction term. The interaction between A and B, should it also be considered as another variable? So those are called as interactions. So I have to really understand what type of interaction should be included. Because if there are three explanatory variables A, B, C, I can include A, B as one interaction term, A, C, B, C. Then I could also include A, B, C as an interaction. This is a three-way interactions. These are all two-way interactions. So I have to really understand what kind of interactions I have to keep in the model, because more the interactions I am including, it is making my model more and more complex. And should there be any kind of non-linear terms included in the model? So just like a is an explanatory variable, should I also consider a squared also as another explanatory variable? A cube also should it be considered as another explanatory variable? So this is what we are calling as non-linear transformations of the explanatory variable. So what kind of non-linear transformation should be used for the different explanatory variables? And if required, do I need to really transform the explanatory variables also? These are the different kinds of preliminary things that you would be looking at before actually initiating the statistical model fitting on the data. And along with that, few things we have to keep in mind. The analysis should be as simple as possible, right? But it should be appropriate to the data and the objective that I have to address. But just for doing this, I want the simplest of the possible. If I have 1, 2, 3 models that are addressing the question along with my data, if one is the most simplest out of the 3 models, then I should prefer one, because I can explain it much better to others compared to a model 2 or a model 3. So for that, what people suggest is initially fit a maximal model. So if what do you mean by maximal model? Okay, if A, B, C are 3 explanatory variables, fit a model in such a way that A separately, B separately, C separately will influence your response variable. Along with that, all possible 2 variable interactions, and along with that, all 3 variable interactions. So this is what we call as a maximal model. We'll see all possible combinations having an influence on your response variable. And after that, initiate a stepwise deletion. Okay, is this not influencing the response variable? Remove it. Is this not influencing the response variable? Remove it. And remove it in such a way that the model gets most simplified, but all those that are there in the model, they are significantly influencing the response variable. So you keep checking the minimal adequacy model for constancy of the variance. This is what we call as homoscedasticity. This is one major assumption that is being taken care of while doing any kind of a model fitting exercise. The variance is constant across the different fitted values, and the errors are also normal. So we can use the plotting of the model. This is one common function that you can use on the model. Any model that you have created, linear regression, logistic regression, any kind of a model that you have created, you can use the plot function on the top of it to understand whether the variances are more or less constant for this model, whether the model is homoscedastic, or you find some level of heteroscedasticity in the model, in the data after fitting the model, which means you need to change the model or you need to make some kind of alternations. And you are also checking for, are the error terms normally distributed? Again, if they are not, then again you may have to rework on your model. And you also would be seeing the standard errors of the various parameters that are getting created, and the kind of effect sizes, to what extent these parameters are influenced, the parameter coefficients of each of your explanatory variables are influencing your response variable. And whatever you are getting through the process, make a clear documentation and explain all the steps that you have taken. So that would be the typical process that is involved when you are going ahead in terms of fitting a model. Then, in this context, we need to understand the term maximum likelihood. So, whatever is the model, let me take the example. We have already said this is a linear regression model. Now, the estimators that I am going to get for the parameters. So, I need to estimate A, I need to estimate B. So, these estimates need to be unbiased, right? The error part should be as much low as possible. So, because of all these characteristics that are expected out of the parameter estimates, we call that kind of mechanism as a maximum likelihood estimation. So, we are making an estimation of the parameters through a process called maximum likelihood. What it means is, if I have a given data, and I know that I have to fit in this particular model to the data, in this case the linear regression. So I am given a data, I have identified that I have to fit a linear regression model to the data. I am trying to understand what should be the value of these parameters A and B, which will make the model, which makes the model observed data most likely. So this particular model, whichever are the parameters of this particular model A and B, I am trying to understand what values of these parameters, right? Should I choose A equal to 1, B equal to 2? What are the values of that parameters of that particular model makes the observed data more and more likely, which means what values of A and B will make this model best fitting to this particular data. Whatever the data set that I have taken, what values of A and B will make the model a best fit to this particular data. So that is what we are calling as the maximum likelihood estimate. So obviously there are so many tools right now, we don't need to get into the theoretical processes of all of them. There are so many tools like R which directly facilitate the process wherein they can compute the maximum likelihood estimates of the parameters. But again, reiterating, when we are doing any statistical modeling exercise, we follow the principle of parsimony, which means the simpler the better. The model should be as much simple as possible. I have to make the model complex only if there is a very high significant value addition that is being provided by adding one or more additional explanatory variables or interactions to the model. So there should be as few parameters as possible. So if I am adding one more parameter, then the intention is it is contributing to the model more significantly. And there is also like a lot of times people say, well, why don't you fit nonlinear models, advanced models? The principle of parsimony clearly says linear models should be preferred to nonlinear models because they carry a lot of explainability of the data. You would be able to communicate and convey the results more and more appropriately when you are fitting linear models to the data. And if there are very few assumptions and I am creating an expressions and experiments, that would be much more preferable than a kind of a model where I have made 100 assumptions. A model where I have made 10 to 20 assumptions should be much more preferred kind of a model to a model which I have made 100 assumptions. So the model with least number of assumptions should be the most preferred kind of a model. And models should be pared down until they are minimal adequate. So just keep cutting down the parameters, keep cutting down the interactions until I get the minimal adequate kind of a model. And simple explanation should always be preferred come to a complex kind of explanation. So all these things I am keeping in mind when I am using a model for fitting it to a particular data. And process of model simplification is an integral part of the hypothesis testing. So a particular variable, initially I have created a maximal model, means I have included all possible variables and their possible interactions, and if possible their next higher order terms as well as a part of the model. I will retain every variable and every interaction as a part of the model only if it causes a significant increase in the deviance. In case that particular variable is removed from the model parameters are changing quite drastically. Right? In that case, I would better retain that particular variable in the model. But if after deleting that particular variable also the change is not significant, then I can very well remove that particular variable from the model. So that's the typical process of simplifying the model. Now let's look at different types of statistical models. Right, one I have already been using, that we would be fitting a maximum model. So just exploring the different types of statistical models. So my objective is to fit a model to the data. So there are no fixed rules of this kind of data. I have to fit this kind of a model only. But finally, it should be a minimal adequate model. So I have large set of models that are available with me. I am selecting a minimal adequate model that can be used for a given set of data. And in that context, one set of models I can use a saturated model where we are looking at for every data point we have one parameter. So it is like if n data points are there, I am having n parameters. So it's becoming equation in n variables and n different equations. So the values you will find one-to-one kind of values. So it's a perfect fitting model, right? It's like I have 3 unknowns and I have 3 equations for them. So I can very well determine the values of the 3 unknowns by solving these 3 equations. So that is what we call as a saturated model. So there is nothing called degrees of freedom, there is nothing called uncertainty. So there is nothing called explanatory power of the model, because it's a exact values, 3 different unknowns, 3 different equations, they are very appropriately fitted to the data. But generally that is not the situation that happens. We will have more number of data points. Data is more compared to the number of parameters that you want to fit. So it's like equations are more in number, but the number of unknowns are lesser. So in that case, it's better to go with a maximal model where I am looking at all the factors of the particular model, their interactions, all of them, covariates. So factors are like categorical variables, covariates are the continuous variables, the interactions, pairwise interactions, three-way interactions, all these different kinds of interactions between the explanatory variables, I can consider all of them as a part of the model. And many of the model's terms, they may be insignificant, and we may have to in later steps, in a stepwise kind of a process, I may be removing all these variables one by one. But various interaction terms might be deleted because they are not contributing significantly to the model. The degrees of freedom will come out as n minus p minus 1, which is n is the sample size, the total samples, which are the data points. P is the number of factors that we are including as a part of the model, factors, interactions, coefficients, all of them put together. That is what we are calling as P. So the degrees of freedom is n minus p minus 1. So the explanatory power of the model depends on to what extent the variation in the response variable is taken care of by the variation in the explanatory variable. Now for these we have different kinds of measures, and R squared is something which is a very common measure that is used in this particular context. Then we are talking about minimal adequate model. We said initially we will start with a maximal model, keep removing the variables in such a way that we will end up with minimal adequate model. So it's a very simplified kind of a model. I'm cutting down the model to the core. It's a simplified model with just P dash parameters. So the P dash will be anywhere between 1 and P. P is all possible combinations, right? All possible interactions, everything. So the simplified model with P dash parameters, which would be in between the two. So it would be a slightly lesser fit compared to the maximal model, because we have removed a lot of variables from that maximal model, but very, very marginal. So what does that mean? If my maximal model is having 100 parameters, and let's say its fitting accuracy is 80%, probably in a minimal adequate model, it will have only 5 parameters. I have cut down all the remaining 95 parameters, but let's say with an accuracy of 78.5%. Now you could see, by cutting down on 95 parameters, simplifying the model, I have just compromised a little bit on the fitment. So we generally prefer this kind of minimal adequate model in this case. So this is what we are calling as minimal adequate model, and in many cases we would be using that kind of models only. The degrees of freedom in this case will be n minus p dash minus 1. The explanatory power in this case, again we are using the R squared as a term, which is the regression sum of squares divided by the total sum of squares. In the regression chapter we would be dealing with these terms in more detail, but this is what would be the way we are assessing a minimal adequate model. Then we also have null model, which means no parameter included as a part of the model. The only parameter is the mean of the model, y bar. So in this case it's only error sum of squares is equal to the total sum of squares. So there is nothing called fitment here. No parameters apart from the constant. So there is no explanatory power of the model. It is going to be a zero kind of an explanatory power associated with the model. And so these are the different kinds of statistical models that we can very well think of. But whatever is the model that we are using, we have to understand that the model is a representation of the reality. So one side, it should be accurate. The accuracy of the model should be much higher, and at the same time it should be convenient. Means it should not be so complex. It should be simple enough. These two are two contrasting features. So that's where we will always look at that particular model, one which is minimal, which is simple enough, but at the same time it is adequate to explain adequate to explain the response variable quite comfortably. So I am using the principles of parsimony, right? We have already discussed them. So in evaluating whether this model is better or this model is better, the simpler it is, the better it is. So and if I have to include one additional variable as a part of the model, it should be contributing significantly to the variation in my response variable. So this part I should always keep in mind while generating any of the models. So you include a new additional explanatory variable in the model only if it is significantly improving the fitness of the model. Otherwise there is no point. Just with a marginal improvement in the fitment of the model, you cannot include an additional variable. So these are some of the points that you have to keep in mind. Whatever is the kind of a statistical model that we are choosing, But in most of the cases, what you observe is either you will be going ahead with the minimal adequate model. That should be the most optimal out of all the different kinds of models. But yes, we need to have a good understanding of all these kinds of models as well. So if I have to make my model simpler, that I have already discussed, you start with the maximal model. All the interaction terms, two-way, three-way, n-way interaction terms, which are all non-significant, start removing them one by one. If at all you have used any non-linear terms as a part of the model, the quadratic, cubic kind of terms, to understand the model, if they are all non-significant, start cutting out all those quadratic, cubic and any other non-linear terms that you have included as a part of your maximal model. Even if some of the explanatory variables, if they are non-significant, start cutting them off. Factors, probably your factor variable might be having 6 different categories, 6 different factors. But let's say factor 1 and factor 4, they are hardly different. More or less the results are looking similar for those two. Then better combine those factor levels if you don't find any kind of a significant difference between those. And even in case of ANCOVA, this we would be dealing specifically in ANCOVA. If the slopes are not significant for various continuous explanatory variables, if they are not different from 0, you can very well set them equal to 0. So with all these things, you can very well simplify the model, make it more and more minimal adequate. And in some cases, even some kind of transformations of the data, some kind of calculations on the data will give me the best overall performance of the model. So I may have to do those things also wherever necessary, right? So now that we know how to make the model simpler, the next thing we will look at is different model formulas that we can use in R. Many a times we have a response variable and a set of explanatory variables. In R, we join them through this tilde operator, which is otherwise called as a formula method. So in a formula method, whatever is the kind of model that we are building, will give a response variable with a tilde sign and followed by a set of explanatory variables. When we are saying something is a null model, means no parameter, it's only one single parameter model and no explanatory variables in this model. That is what we are calling as a null model. So the way we fit a null model is the y, which is a response variable, tilde 1, which will take the overall mean of y. That's the only parameter that gets worked out. Those kind of models are called as null models. And a regression model, y tilde x, where x is a continuous explanatory variable and y is a continuous response variable. And if I want the regression through the origin, means in a typical regression, I will get something like y equal to a plus bx. So this is the intercept, this is the slope. But if I don't want this part, this is what we call as regression through the origin. So we will set the model as y tilde x minus 1. So x is the x variable, minus 1 says don't fit the intercept term. So make the model as y equal to bx kind of a model. In that case, it is called as a regression through the origin. We are not fitting the intercept to the model. Then, when I have to fit in a one-way ANOVA to my model, I will set it as y tilde this variable x will be a factor variable. In that case, I will call it as a one-way ANOVA. But if I am talking about two-way ANOVA, I am having two different factor variables. Both of them are separated with a plus sign. And if I am having a factorial ANOVA, I am looking at all the variables. Let's say I am talking about 3 variables which are all factors. So n, p, k are 3 different factors. but I'm also looking at all kinds of interactions between them, means NP, NK, PK, NPK. So it becomes N plus P plus K plus NP plus NK plus PK plus NPK. So that is what we are calling as factorial ANOVA. So we are trying to fit the y, the response variable, we are trying to link with all these interactions. So the factors are fitted along with all their interactions in a factorial ANOVA. Now going with a three-way ANOVA, it means that I am looking at the three variables and their pairwise interaction. So we are looking at NPK. So which is like, this is the factorial ANOVA minus, when I said N colon P colon K, I am not looking at the three-way interaction. Out of all the possible things like this, I am removing this part. So the three-way interaction, so this is an indication of the three-way interaction. So the two-way interaction will be represented as N colon P, P colon K, whereas the three-way interaction would be represented like this. So out of all the possibilities of factorial ANOVA, I am not considering NPK. That is what is my three-way ANOVA. Then if I have to fit ANCOVA, analysis of covariance, I am setting the formula as y tilde x, which is a continuous variable, and one factor variable. So it's a common slope for y against x. So the slope is common, but intercepts are different for different factors. Right? The slope will come out to be common. So the x parameter of x will be the same. The slope will come out to be common here, but each you will get different intercepts for different factors. So which means you are getting multiple equations, one equation for each factor. That is what is coming out in analysis of covariance. Similarly, if you are talking about analysis of covariance where I am having x multiplied by factor, if I am putting it as multiplication here rather than plus, it is like both this will be different, this will also be different. So the slopes will be different for all the factors, and even the intercepts also will be different. So in analysis of covariance, I can do two things. One, I can keep the slopes constant, and I can make the intercepts differ across the various factors. Or in some cases, I can have both the intercepts as well as slopes differing across the factors. So you have to be clear based on the kind of objective we would have to fit the appropriate model. Then we also have a split plot ANOVA where we are taking a factorial ANOVA here, right? We are looking at the relationship between y, the response variable, and a, b, c, the factor variables along with their interactions, but along with that we are also giving an error term. Three different error variances, conditional error variances is what we are giving, which is what we would be representing as A conditional on B, conditional on C. So it's a factorial experiment only because we have given A star, B star, C, but we are getting three different plot sizes and three different error variances here. So for each different plot size, we are having a different error variance that is being considered. Similarly, then we are talking about multiple regression. Y is the response variable, x plus z are the explanatory variables, x and z are both continuous explanatory variables. And if I am putting a star, it means I am considering along with x and z, I am also considering the interaction between x and z as well. And this is one more way of multiple regression where I am looking at x plus I of x squared plus z plus I of z squared. So I am actually considering the quadratic terms x squared and z square also. Instead of just considering y with x plus z, a normal multiple regression, I am also considering x squared and z squared also. So we will put, wherever we are considering the squares and other non-linear terms, we will put I of as a part of the model, which is as which means same as. So it fits a quadratic term for both x and z. Similarly, if I am saying polynomial x comma 2, so it's like a quadratic polynomial, but z is more of a linear. So I can very well set the polynomial for x, whereas for z it should be more linear. So even this is one more way I can fit my multiple regression equation. So this is one more way of creating a multiple regression equation, x plus z plus w whole square, which is saying you will consider all these variables x, z, w. You will also consider their interactions, but only up to two-way interactions. Means you will consider xz, xy, xw and zw, but you will not consider xzw because it is only up to squares. You will have only two-way interactions between the variables. Then we also have non-parametric models, right? You would see them as a part of generalized additive models also. The non-parametric models, where you will take the smoothened value of x and smoothened value of y. We will try to fit in the relationship between y and the smoothened values of x and z, which you will find as a part of generalized additive models, which we would be taking up to understand these relationships as well at later point in other sessions. And we also have the transformed response variables and explanatory variables. So I have done a logarithmic transform for y. I have fitted the x. I have taken the 1 by x, which is the reciprocal transform we have performed for x, and we have also looked at the square root transform for z. So all the variables are getting transformed, and those transformations is what we are using as a part of our model. So all these are different kinds of model formulae that I can use in R. Now in all these things, whatever you are looking at the right hand side of the tilde sign, so we are looking at different explanatory variables. So I am exploring how many explanatory variables are there and what are those types of those explanatory variables. Are they continuous? Are they factors? What is the level of interactions that are existing between the explanatory variables? Is it a two-way interaction, three-way interaction? What is the level of interaction that is present in the explanatory variables? And even if there are some kind of non-linear terms in the explanatory variables, squares, cubic kind of terms, or if they are there as a part of the explanatory variable. And in some cases the explanatory variables are coming not in their original form. There are some kind of transformations also that are coming for the explanatory variable. Typically the logarithm, the exponent, the square root, the reciprocal, etc. So the explanatory, this is the commonality. This is these are some of the important aspects that we are observing when we are building the model formulae in R. But whatever are the models that we are building, these are some of the common ways in which I can represent these models as a part of the various R formulas. So in this, if you see, wherever we are using the plus sign, it means I will include that explanatory variable as a part of the model. But if I am putting a minus sign, I will delete that particular explanatory. I will not include, or I will remove that particular explanatory variable from the model if it is already included. Wherever the star is set, I am taking the explanatory variables along with all their interaction. So if there are three explanatory variables, I am setting A star, B star, C. Then I am looking at all the interactions along with a single A, B, C. I also look at AB interaction between AC, BC as well as ABC. So that is the meaning of star. But if I am putting a slash, I am putting the nesting of the explanatory variables. So here it is, this is what is meant by nesting. If I put A slash B slash C, it's like A. So those values of B which are also in A, right, those values, so initially I am taking A, those values of B which are also in A, those values of C which are in B, and those values of B which are in A. So this is what is the conditionality. I am including those things of C if they are in B, including those things of B if they are in A. So we are putting a nesting of the explanatory variables in the model. But if I am putting it as a piping symbol, I am conditioning. Means I am building a model between Y and Z, Y and X, but given a particular value of Z. Given this is Z is some specific value, so which means only for those specific values of Z, this model is applicable. So if I am saying Z is gender, so for a male there is a separate model that is getting built between Y and X. For females there is a separate model that is getting built between Y and X. So that is what we are calling as a conditioning variable. Right, so we will have conditional models that are getting built, and if I am putting colon, it means it's an interaction. So just for example, A star B star C is nothing but A plus B plus C plus A colon B, A colon C, B colon C, A colon B colon C. And if you are raising it to the power 3, it means that you are using all the interactions up to the third interaction. So, but when you are putting only 2 whole squared, it means you are taking only up to the second interaction. So between these I am taking the whole factorial representation, but I am not including the three-way interaction between the variables. So these are some of the symbols. When you are giving them as the inputs into the model building exercise, you have to be very comfortable with the usage of these various symbols. Now, the next important topic that we are looking at here is Box-Cox transformation. Very, very important. If I have so many different kinds of explanatory variables and each one of them is having a different distribution altogether. So this is performing an optimal transformation of the response variable. So we are trying to look at an optimal transformation of the response variable. So generally I was talking of earlier that we will do a log transform or we will do a reciprocal transform of the variable. Now here I can very well go ahead in terms of a very generic kind of a transform called the power transformation, wherein we use something like this: y power lambda minus 1 by lambda. Now let's say if lambda is equal to half, so what is it becoming approximately? Y to the power of half minus 1 by half. So it is approximately becoming 2 into y to the power of half minus 1. So it is very much similar to that of a square root transform. Right, we are taking the square root of it, then multiplying it by 2 and so on. Similarly, if y is equal to 1, if lambda equal to 1, then it means y minus 1 by 1. So it's actually we are keeping the y in its original form itself. But let's say lambda equal to minus 1. It's as good as y to the power of minus 1 by minus 1. So it's more or less similar to I am doing minus 1 by y. So you could see, depending on the kind of lambda, different kinds of transformations are being tried out, and we are looking at that particular value of lambda that maximizes the likelihood. So when we are fitting a specific set of explanatory variables to this transformed value, so which particular set of which particular lambda value will maximize the fitment of the particular model to the transformed data. So that is what is the Box-Cox transformation. The lambda value can be either positive or negative, but not 0, because if we are setting it as 0, it is y to the power of 0 minus 1 by 0. It's an undefined kind of a form. So what the Box-Cox transformation does is, if the lambda is coming out to be 0, we would be taking it as logarithm of y. And this Box-Cox transformation can be performed using the mass package of R. So once I load the mass package, I can use a simple function called Box-Cox, wherein we are setting y tilde x plus z. You will get that particular value of lambda where the likelihood of y with respect to x and z is maximized. Much more than that, we have a very interesting function of Box-Cox as a part of the forecast package. So what we can very well do is, so it is a function called Box-Cox.lambda of x, which will apply the lambda value. Right, this is a two-step process. You see, first we are talking about Box-Cox.lambda of x. So we are applying whatever is the lambda that we are getting on the data so that the transformation is performed. So the Box-Cox as a function is performing the Box-Cox transformation of the data based on the lambda value. And this Box-Cox.lambda is finding out that particular value of lambda which is maximizing the likelihood. And probably if required, we are even scaling the data also, so that the size related errors also get narrowed out. So this kind of a transformation is what we are calling as a Box-Cox transformation. So this could be more comfortably be used rather than just relying on the Box-Cox from the mass package. So it will be auto transforming the data. So this is the kind of a function I can write to auto transform the data to its Box-Cox transformation, where the best possible lambda would be identified and based on the maximizing of the likelihood. And that particular lambda value could be different for each of the column, and that is what we would be using for all our prediction purposes, right? So our data is getting transformed so that we are getting the best fit representation as a part of our model that we are fitting to the data. Now, regarding the criticism regarding the models, some of few truths that we all need to be understanding about the models. All the models are wrong. It's not I will get 100% accuracy by fitting any kind of a model. The only thing is some models are better than the other. And there is nothing called this is a correct model, this is a wrong model. I can never find out that this is a correct model or this is a wrong model with certainty. I can only approximate things, saying that this model might be a better model for this kind of a data. That's the only thing I can say. I cannot say that this is a perfect model for this kind of a data. And as I have been talking about right from the beginning of this session, the simpler the model is, the better it is. So there are some of the common to-do kind of stuff which we suggest. If at all I want to improve my model, if at all I want to increase the accuracy associated with the model, some of the common kind of processes that I generally suggest is try the transformations of the response variable. Probably you can use the Box-Cox transformation of the response variable by using an appropriate lambda to it. And if required, perform similar kind of transformations on one or more explanatory variables. And if required, try fitting different explanatory variables. If your current explanatory variables are not sufficient, you keep adding. If you are able to collect some more explanatory variables, you keep collecting those explanatory variables, and you can fit those different explanatory variables to the particular, you can fit your model to those corresponding explanatory variables. Then a different error structure. There are different ways of looking at the errors. Earlier we were talking about the least squares kind of error. Then we can also talk about log likelihood. Log likelihood could be the mechanism associated with the error structure. If required, I can change the error structure and I can use a different error structure to improvise my model. If at all my parametric functions are not doing a good job, there is a lot of there are a good number of outliers in my data. There is a lot of variation that is present as a part of my explanatory variables. If required, better go ahead with non-parametric smootherers that could be used rather than directly using the parametric variables on the data. And one more step that is suggested is, if possible, you could also use, don't treat all the data points with the same kind of weight, right? All the values of your response variable don't give a same kind of a weight. Probably you can alter the weights, you can weigh them, right? If the values are between this and this, you can give some kind of a weight. If the values are above this, you can give some other kind of weight. So these are some of the things which you can definitely do to make some kind of improvisations to your model, so that you can use them in the real world for understanding your data much better. A few more things, especially if I want to really look at the inadequacy, right? I don't know whether the model is sufficient enough to explain my response variable or not. So I have a set of tools which can really look at the evaluation of the model, see whether the model is adequate enough for explaining the response variable. So there could be a possibility that some values of y, right, if there are 100 records that I have taken, it might be very well possible that almost 90 records are predicted more or less fine, but there could be some values of y which are not being predicted properly. So that it means that there should be something else as a part of the model which is not getting captured, especially some specific values of y are not getting predicted properly through the model. Even the variance is not constant. This is what is a scenario of heteroscedasticity present in the model. So we have to really see and understand, how do I really address this scenario of heteroscedasticity. Generally what we find is, if I am trying to plot a graph between my predicted values or the fitted values, and if I am looking at the residuals here, I could see that the error terms at different points, probably when as the fitted values are increasing, as the value of the fitted values is increasing, the error terms are getting more and more widened. So there could be a lot of non-constant variance that could be there as a part of the model. Similarly, there could be non-normal errors. We are saying that the errors should be more and more normal in nature. There is a possibility that the errors are, if I am plotting a Q plot for the errors or the residuals, they will not fall on this 45-degree line, which could be an indication that there could be a lot of non-normality that could be present in the error term. And there could be a lot of influential data points, means if there are 2, 3, 5 data points, wherein if I am just removing one of them, the whole model gets completely distorted. The whole model, the interpretation of the model becomes completely different. So those are called as influential points. So the model could be very well influenced by small number of the data points. So the moment when I include that point, the interpretation of the model is something. When I exclude the point, the model interpretation changes drastically. Those are called as influential points. So if there are there are one, two, few influential points as a part of the data, then also I can say that my model is inadequate. I have to really improvise on the model. And if there are some kind of systemic patterns, so basically my residual should be as much random as possible. There should not be any kind of a pattern as a part of the residuals. So if there is some kind of identifiable pattern as a part of the residuals, which means there is a scope that I can very well improvise on the model. And there is a lot of over dispersion, lots of variance that is being displayed, which also indicates that a huge improvisation to this particular model has to happen. So these are some of the common observations, irrespective of whatever is the kind of model you are fitting, whatever is your objective. These are some of the things that you have to keep in mind when you are creating or fitting any kind of model to a particular data set. Then, once you have created your model, you have found that this is an appropriate model for this particular kind of a data that you are using. Then you also look at goodness of fit, right? Goodness of fit again can be performed through various mechanisms. So you look at a couple of observations. So you make a goodness of fit versus a couple of observations. You probably test them on those observations and you can say whether your model is good or not. You can fit them against one or more explanatory variables. You change the values of one or more explanatory variable and see how the response variable is getting affected. So we can see the systematic trends in the goodness of fit, and based on that we can say whether my model is anywhere close to accurate or not. Generally we plot some kind of graphs. We do a fitted values. So we will plot, as I was talking in the previous slide also, I'll have the fitted values here and the residuals here. So they have to be more or less randomly spread out. But if they are not randomly spread out, and if I see some kind of a pattern that the error is increasing when the fitted values are increasing and errors are much lesser when the fitted values are smaller, that's a typical case of heteroscedasticity that is present in the model. As the value of the fitted values are increasing, even my residuals or the error terms are also increasing. So that's one thing that you can put out. You can also create a plot where you take the explanatory variables on the x-axis and you plot the residuals on the y-axis. So this will tell you whether some kind of curvatures are there as a part of the graph. So if required, you can include the quadratic terms and the cubic terms also as a part of the model building exercise. So even this kind of stuff you can very well do to check the appropriateness of the model. Then you take the sequence of data collection. Especially if you see, especially with the time series related data, it matters a lot. But you can check the sequence of data, probably the first row versus the second row versus the third row. You can very well check for the presence of correlation that is present across the error terms. If the correlation is present across the error terms, that is what we actually call as serial correlation. So we will be checking if there is some kind of serial correlation that is present in the data. And you will also take the standard normal deviates versus the residuals. For different standard normal deviates, you are plotting the residual, which is more or less similar to your QQ plot, to really see if the error terms are having any level of non-normality present in them, which requires that Probably I may have to do some kind of transformations before using a variable as a part of my model. So some of the important aspects of model checking, and again these are some of the points which I have to see in any scenario. Then heteroscedasticity generally obtained through this kind of plot. If I'm talking about a good model, so the variance versus the mean relationship is taken care of adequately, which means there is no specific pattern in the variance versus the mean. Even as the mean of the fitted values is increasing, I don't see any specific pattern in the variance of the term, variance of the residual. So then it is called as a good model. So you are plotting the residuals against the fitted values. If they come out to be fully scattered with no specific pattern, then it means the model is decent enough. But generally what we observe is the variance will start increasing with the mean. You will find that very large errors are there for higher fitted values, and the errors will be very small for lower fitted values. That is what is the scenario of heteroscedasticity. To whatever extent possible, I have to remove the heteroscedasticity from my model. So that's one more activity for me as a part of the model checking process. Then my errors could very well be non-normal. So there could be skewness, they could be positively skewed, negatively skewed. There could be a high amount of kurtosis, either platykurtic or leptokurtic. So I could see some kind of high skewness, high kurtosis, low skewness, low kurtosis, or both kind of thing, which is a clear indication of non-normality of the errors. So our interpretations will get very biased if there is heavy amount of non-normality that is present in the data. So by looking at the QQ norm and the QQ line, I can very well look at the normal plots. I could see to how much extent the errors are deviating from normality. Or I could also use traditional tests like Shapiro-Wilk test, which is typically obtained through Shapiro.test, which will tell me whether this particular set of data is normal or non-normal. So I could also have a plot of the model. So generally model plots, there are 4 different plots that come, especially if it is a linear regression model. When you are saying plot of that particular model, you will get 4 plots, out of which one of them is your typical QQ plot itself. So from that QQ plot also you can make out whether your data, whether your errors are more or less normal or not. Then once you understand the model checking process, then we are looking at the points which are called as influencing points. So we know if there are too many outliers, outlier itself means my model accuracy will be very badly affected. Right? If an outlier is present, the fitness of the model will become very poorly, poor, which means I may not be fitting an appropriate model to the data. So more and more outliers there, my model accuracy will become much poorer. So here I would be looking at these influential points. If there are influential points, if you say, okay, all these are the regular ones, but here I have an influential point. Suddenly what happens is, if I am including this also as a part of my data, originally my model would have been something like this, but because of the influential point, my model might be becoming something like this, because this is influencing the model very heavily, that it is pulling the line more closer to it. So it's always necessary that I will test for the presence of influential points as a part of my data, which is very essential step in the statistical modeling process. So whatever we take as a model, we can very well use the function called influence.measures. So it will give me the most extreme values of the explanatory variable. Right, it will take those extreme left, extreme right kind of values of the exclamatory variable, and based on that it can even highlight them with an asterisk, which means you have to give, they are the very influential points for this particular model. You have to really handle them. You may have to remove them, because that one single value is either creating very heavy influence for your model, or immediately your model interpretation is getting completely changed by inclusion of that versus by exclusion of that. So you could very well use this influence dot measures, and I can say ease dot inf, which will tell me how different the influential measures are treating each of the points. So when we are creating the models, we would be using all these things. So how different influential measures are treating each point, right? There are different kinds of measures we can use with respect to influential, finding out each point how much of influence is it creating, and based on that you can see which points can be included versus which points can be very well removed from the model, right? When I am doing a lm dot influence of a model, so I will get an input called $hat. I can give $hat, where I will get the hat matrix and the diagonals of the hat matrix, which talk about the leverage of my response variable. So if the leverage value is very high, means if that particular point is removed, immediately my model will be changing quite drastically. So if the $hat value is much higher for a particular point, it means it's a very highly influencing point. And if that particular value, it means that if that particular value is tampered to some extent, my model will be completely changing. My model will be a drastic change. So I have to really see what is the accuracy of that particular point. And in that lm influence, I would also get the coefficients, which will tell me if that particular point is dropped from my model, what would be the change in the coefficients of the model. So if I am dropping a particular point, so if I say my coefficients will fall by 20%, so there is a kind of influence of that, if that influence is really significant or not. Even that aspect is also being brought out by the coefficients of your lm dot influence model. And similarly, the sigma is also being brought out. What would be the residual standard error? So will it be reduced drastically, or is it increased if I am typically dropping that point? So basically it's like, if I am having this point as an influence point, let's say I am dropping this point and I am rebuilding the model, by what extent the coefficients of the model will change? That's one point that I am looking at. By what extent the residual standard error of the model will change? And if at all there are any kind of weighted residuals, if weights are not set, it will just give me the raw residuals, but otherwise if I have set any kind of weights to each of the observations, I will get the weighted residual values. So this way I can identify which particular variables are, which particular points are very heavily influencing my model. So based on that, if required, I may really take them out of my model, so that more and more reliability can be assigned and attached to the model that I am building from the data. Alright. Now here we will look at a summary of different statistical models in R. So if I am using a function called lm, my intention is I am fitting a linear model. I am assuming that the errors are normal. I am also assuming that the variance is constant. So there is no heteroscedasticity that is present, right? So it is homoscedastic, and the errors are coming out to be normal. So the QQ plot looks more and more normal, more or less a straight line kind of a stuff. So this is what, for this kind of a purpose, I will use lm as a function to fit a linear model. So generally when my objective is to do a regression analysis where all the variables are continuous explanatory variables, all the explanatory variables are continuous, no factor variables there. In that case, I can very well use the LM function because in that scenario, I am fitting a regression analysis model. Then, the next function that I should look at is AOV, which is nothing but analysis of variance, otherwise called as ANOVA in short. So this also assumes that my errors are normally distributed. There is no heteroscedasticity with respect to the error terms, and I have the identity link. We'll talk about it when we are using the ANOVA. So when my variables, explanatory variables are more and more categorical, then I would be using this AOV as a function on my data. And similarly, if my data has a mix of both categorical as well as continuous variables, then I can use it as ANCOVA. So both of them are facilitated through the same kind of mechanism. So AOV can be used to perform ANOVA as well as ANCOVA, depending on whether my data, whether my explanatory variables are more of factors or a mixture of factors and continuous variables. Then if I am using GLM as a function, it is like I am trying to fit generalized linear models to the data. So you will find good set of models coming under the generalized linear models. So as the word itself is saying, it's linear models, but we are talking about generalized linear models. So in this case, my explanatory variables to be either categorical or continuous or both. But here I will specify different kinds of error structures. So if my data is a count data, the error structure that I will specify is a Poisson error structure. If my intention, if my response variable is just a continuous data, then I may specify the error structure as normally distributed error. If my intention is the response variable is a proportion data, if I am trying to model a proportion data, then I will specify the error structure to be binomial. So here what is that I am doing? My explanatory variables could be either continuous or categorical, but along with that I am also giving an error structure, and the error structure again, depending on my target, depending on my response variable, I'll be choosing an appropriate error structure. So more commonly, if my data is, if my response variable is a count data, then I'll use a Poisson error structure. If my response variable is a proportion data, I'll use a binomial error structure. So we can fit GLM models to your data. Similarly, I can think of GAM models, which are generalized additive models. Again, we can have one or more error structures. So generalized additive models, here the only difference is instead of taking the variables as categorical or continuous explanatory variables, they are taken as arbitrary smoothened functions. So there are non-parametric smoothers that are coming up. So instead of taking them as continuous variables or categorical variables, especially the continuous explanatory variables, they would be smoothened using non-parametric smoothness. So that's where your GAMs are more and more of non-parametric kind of fitting, corresponding to your GLMs, which are more and more of parameterized kind of fitting. So you can have either of the fits to your data. So if your explanatory variables are very much deviating, very much outliers, in that case, it's always better that you can look at your GAM models rather than the GLM models. Similarly, another set of models that you can use are LME and LMER, especially if I am interested in linear mixed effects models. So when I am saying mixed effect, so for some variables, if we will have fixed effect, and for some variables we'll have random effect. So what it means is it might very well be possible that if I'm talking about variables A, B, C or X, Y, Z, I may have X and Y to be fixed, whereas Z could be random, which means so the coefficient for X and Y will be same for everyone, for all the data, for all the groups, whereas the coefficient of Z could be different for each of the groups. Now this is where we are bringing in the random effects as well. So you can easily specify the correlation structure among the explanatory variables, and based on that you can even change the equations of each of the variables as well. And even if the error terms are very much non-normally distributed, and even if there is a lot of heteroscedasticity that is present in the data, I would suggest that you should look at LME and LMER models rather than relying on LMs and ANOVA kind of model. So if your explanatory variable is way deviating from this, you can very well rely on LME and LMER. Similarly, the other set of models that you can look at is NLS, which is like a non-linear regression model, right? So you can very well fit a non-linear regression model using the method of least squares, and the parameters are based on the non-linear function that you are specifying itself. So if you want to fit a non-linear regression model to your data, you can very well use NLS, whereas LM is used for linear regression model. NLME, again, it's a non-linear but again mixed effect model, which will have some variables carrying a fixed effect, some variables carrying a random effect. So that's just like LME, we have NLME. LME is the linear mixed effect model, NLME is the non-linear mixed effect model. Then we can also have Loess models, which is where I am fitting a local regression model and I am having one or more continuous explanatory variables, and the smoothing is also happening. So it's a regression model, but there is some level of smoothing also that is happening over the explanatory variables. In that case, I am fitting a Loess kind of a model. Then the tree models, we are fitting a regression model here using a binary recursive partitioning. It would be much more appropriate when I am discussing those things in detail. But again, this is also another kind of a model. We can have a tree kind of a model wherein I can very well link my output variable to a set of inputs through this a tree kind of a structure. Right, so it can be a tree kind of a structure. So the data is successively split like this along the coordinate axis of the explanatory variables. So this is chosen. So probably the value is chosen in such a way that this branch is very much separated from this branch. So that is one more, when we are fitting a tree to a particular data, this becomes more and more comfortable. But just for having a summary of the different kinds of models, I am trying to bring it. So this is what we call as classification tree, where my response variable is categorical in nature. I am trying to predict, I am trying to model the default of a person, whether he will default on a particular loan or he will not. So yes or no, to model that yes or no, we can very well use a classification tree kind of a structure. So this kind of models, they assume that the response variable follow a multinomial distribution, and based on that the whole results will be computed, and the model parameters would be estimated accordingly, right? Then, so any kind of model, now we have talked about at least 10 to 15 different kinds of models. So each model is coming out as a part of a different session, right? When I'm talking about a session on linear regression, then probably I would be using LM as a function. When I take a session on ANOVA, I would be talking of AOV as a function. So like that, almost one different session will use one different function out of that list that I have highlighted. But few things are very common across all those models. Let's say if I have used LM and created a linear regression model, or I have used NLS and I have created a non-linear regression kind of a model. Whatever is the model that I have created, on the top of that model, when I am doing a summary, I will get the parameter estimates. Right? When I am putting summary on the top of that model, I'll get the parameter estimates of that model. So the coefficients, the various coefficients of the parameters, and the standard errors associated with them. So those are the things that are produced through my summary function. When I am doing a plot of that model, I'll get the diagnostic plots, especially for checking the goodness of fit of the model. So we have seen that all the residuals will be plotted against various aspects. Normality checks of the errors would be performed. I can see the influence test. Any specific points are significantly influencing my data, influencing my model or not. So those are the various things that we can easily make out by checking the plot on the model. When I'm using ANOVA on the models, especially let's say if I have built 3 models for a particular data, by adding more and more variables to it, I can really compare the models, seeing which model is the best out of the 3, or is one model significantly better than the other model. So doing a model comparison becomes more easier if I'm using ANOVA as a function on the top of the model. Then if I'm using an update function on the model, it means that I'm modifying the last built model. Whatever the model that I have fitted, I'm trying to modify it. I'm trying to either remove one of the variables from it, I'm trying to add one of the variables to it, whatever it is. So I am trying to do some kind of modification to that model. And when I'm using a function called coef of the model, right? So anything, these are the functions. So it gives me the all the parameters of the model that I have typically fitted. And fitted of the model will give me, so for all your current explanatory variables that are there, so it will take those explanatory variables, it will take your model formula, and it will try to fit the values of your response variable based on the explanatory variable and based on the model that got created. So it gives the fitted values. If at all you don't know what are your existing response variable values, you have your explanatory variable values and you have the predicted model. What would have been the values of that response variable is what is typically being computed and presented to us when we are using the fitted of the model. Similarly, when we are talking of the residuals, it is like actual value minus the fitted value. For each of the observation, it will compute the actual value minus the fitted value, and that is what is being presented as the residuals of that model. And I can also use another function called predict, especially when I am having another data set altogether, a new data set, and I want to fit the model that got created here to this particular data set. I can very well use the predict function so that I'll get the results, the response variable of this predicted data set. I can get the response variable associated with that particular data set. So these are some of the most common functions that you will use on any model, whether it's a linear regression model or logistic regression model or non-linear regression model, or for that matter any of the models that you are selecting. You can use any of these or all of these functions on the top of those models, and more or less you would get similar kind of results. So that's why we call them as generic functions, so that I can get a more common kind of an information out of each of these models quite comfortably. Now, the next point that we need to understand in this session is Akaike information criteria, which is in short called as AIC, which would be computed for different kinds of models. So if I want to compare model 1 and model 2, I can very well use the Akaike information criteria as a base for comparison of the model. Now what this AIC typically does is it penalizes the log likelihood. More the number of parameters, right? If I have more parameters as a part of the model, it puts additional penalty to the computation. If you see here, AIC is getting computed as -2 times log likelihood plus 2 into p plus 1. P is the number of parameters. So if the parameter is high, if more number of parameters are there, I will get 2 into p plus 1 value to be much higher. So log likelihood of the model, it is calculating the log likelihood for any object, and AIC is getting computed based on the log likelihood along with 2 into p plus 1. So it is a measure of the fitment of the model. If I am having 2 models, 3 models, I have to compare between the models, then AIC comes into picture. More parameters if they are there, we know that it is a better model because R squared would be much higher, explanatory power would be much higher for that model, but that explanatory power, if it is very marginal, very limited, then what it says is better don't add that parameter at all, better don't add that variable at all. So AIC is a kind of a trade-off, one between the goodness of it, which will keep increasing by adding more and more parameters to the model. So there is no way the goodness of it will come down with the increase in the number of parameters. But the second part is parsimony, that is making the model more and more complex. So it's a kind of a trade-off between the goodness of it versus the parsimony. So if the parameters are very superfluous in terms of if that parameter is not there, if we say the accuracy of the model is this much, but by adding that parameter, let's say this is the increase in the accuracy of the model or the goodness of fit of the model, then this is a very marginal increment. So this 2 into p plus 1 is actually penalizing it, because I will choose a model that is having the least possible AIC. So if the parameters are more higher, the AIC value will start increasing, so the model would be going out of choice. So when I am comparing two models, I have to look at that particular model that is having the least possible AIC, because based on the AIC I would be saying that kind of a model is a much better fitment of the for that particular data set. So I can use the function in R like AIC of model 1 comma model 2, which will be used for comparing two different models. And even when I am automating, let's say I have developed a maximal model, and after that I am starting to remove all the variables or interactions between the various variables. So the way the variables are removed in a stepwise kind of a fashion is also based on AIC only. When I am using my step function, I could see that it has removed a particular variable from the model or it has removed a particular interaction from the model purely based on the AIC as a criteria itself. So in general, we should understand that AIC is a kind of a criteria which we are using to compare two models. So now that we got a good understanding of all these activities, quickly summarizing, if I have to create a statistical model, what are the various steps? My first step always is inspect the data. So first go with one variable analysis, then probably you look at the variables in pairs, look at different kinds of plots, tabular summaries you want to create, look out for errors that are there with respect to data entries, etc. Identify different possible outliers that could be there in the data. So let all that be one step. Then identify what is a good model for this particular data. So we have seen that there are n number of models that are there for addressing different particular aspects. So based on the data, based on the questions that you want to address, choose an appropriate model. And once you have chosen an appropriate model, you specify what are the fixed effects and what are the random effects. If at all there are some kind of random effects associated with this model, a few variables for which you want the coefficients to be more and more random in nature, you select those particular variables as well. So initially go ahead with the maximal model where all the explanatory variables and all their interactions and if possible all their quadratic cubic aspects also get included as a part of the model. Along with that, specify the appropriate error structure also. As we have seen, if it is a count related response variable, it's better that I use Poisson error structure. If it is binomial or if it is a proportion related response variable, then I can use binomial related error structure. So depending on the kind of output data, depending on the kind of response variable, I can select an appropriate error structure. So once I have a maximal model, I can very well start simplifying it by deleting all those non-significant interactions, non-significant nonlinear structures, non-significant variables. Try to simplify the model as much as possible and try to evaluate the model critically, get the diagnostic plots of the error terms with respect to the normality of the error terms, with respect to the constant nature of the error term variance, and also you could see if there are some kind of points which are influencing the model quite heavily. All these various aspects you can look out in the model and improvise the model and again repeat all these steps as long until you get one of the best fitting kind of model. So that is the typical process. So when we are doing real modeling using different kinds of techniques, all this framework, all this pattern that we have discussed will come in more and more handy for us. So these are the various aspects that we have discussed as a part of this session. If you have any further queries regarding any of the aspects of this session, you can very well give me a call. You can give me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.